All right, so let's continue. Basically, let me just sort of go through the first few steps that we had. So the first step was to convert the problem into standard form by adding slack variables x3 and x4 to the first and second constraints respectively. And then we added a new variable, which we called z, and z corresponds to the objective function value. So z satisfies z is equal to minus 3x1 plus 2x2. Then I can put everything on the left-hand side, so I obtain a new equation. So I have my original 4 decision variables plus the fifth one that I just described, which I defined, which is the z variable. Then I'm writing it as a system of equations, basically. Okay, so I mean, there's nothing special so far except that we just defined new variable z. So this is all. I mean, there's no new stuff here. So what I'm going to do is the following. So since z is a special variable, I'm going to draw a line here. I'm going to separate it from the rest. Okay, so z is a variable that I defined, so I'm going to put a line over there. The right-hand side is also special, right? I cannot control that. I'm going to put a line over that as well. Then just to sort of separate the variables from the rest, I'm going to put a line over here. Okay. And finally, since the first equation is something that I defined, I'm going to put another line over here just to sort of differentiate it from the constraints. Okay, so anything that sort of remains below this line corresponds to constraints, and anything in this row corresponds to the objective function, basically. Okay. All right, so now the first column, in other words, column corresponding to z, is special and will never change. So I will never make any operation on the first column. Okay, the first column always will be 1, 0, 0, basically. Okay. So now if I look at this as a system of equations, so let me look at the columns underneath z, which is 1, 0, 0, underneath x3, which is 0, 1, 0, and underneath x4, which is 0, 0, 1. Okay? So if I only look at my variables z, x3, and x4, and if I look at the columns underneath those variables, then it's not too hard to see that that system will be in canonical form, basically, right? So I have the identity, the first column of the identity matrix here, I have the second column of the identity matrix here, and I have the third column of the identity matrix over there. Okay? And we know that, you know, whenever we define a set of basic variables, the columns underneath the basic variables should be linearly independent, basically, right? Okay? And as a result, if I pick my basic variables to be z, x3, and x4, then the columns underneath are linearly independent. Why is that? Because the columns underneath those three variables are just the identity matrix, basically, right? Okay? And the identity matrix is very invertible, right? So as a result, I can pick z, x3, and x4 to be my original basic variables. Okay? So what I'm going to do from now on is that since z is the column under z does not change, so since z will always be part of the basic variable, I'm not going to count it as a basic variable. Okay? So I'm going to just count the decision variables, or which decision variables are basic. So I'm going to simply define my basic variables to be x3 and x4. Again, implicitly you should think that z is also a basic variable. Okay? Then my non-basic variables will be given by x1 and x2. So now when I look at the B matrix, again I'm going to look at my B matrix from the original A matrix. Okay? So the A matrix corresponds to the constraints, so I'm going to pick my B matrix from this matrix over here. Okay? So when I look at my B matrix, I'm again ignoring the first row. Okay? I'm just looking at the second and third rows. So what's my B matrix? Well, B matrix corresponds to x3 and x4, so it's going to be given by the identity matrix, so which is 1, 0, 0, 1. And my N matrix, which corresponds to the first two columns of the A matrix, will be given by minus 3 and 3, minus 4 and 2. Okay? So just like we did earlier, I'm going to set all the non-basic variables to 0. And I'm going to solve for the basic variables, which are x3 and x4. And they're given by b inverse times little b. But B is just the identity matrix, right? So its inverse is also the identity matrix. What's my little b? Little b is 6, 2, so as a result, this will just give me little b itself, which is 6 and 2. Okay? So as a result, the corresponding solution will be given by x1 is equal to 0, x2 is equal to 0, x3 is equal to 6, and x4 is equal to 2. Now, is this a feasible solution? Yes, because all the variables are non-negative. And furthermore, this is a basic solution at the same time, right? So as a result, we get a basic feasible solution. Now, what's the value of z corresponding to this solution? Well, if I look at the new equation that I have, so z plus 3x1 minus 2x2 is equal to 0, or in other words, z is equal to minus 3x1 plus 2x2, but both x1 and x2 are equal to 0, so as a result, the value of z will be equal to 0 as well. Okay? Now let me come back to this tableau again. So the value of z is equal to 0, right? If I look at the right-hand side of the first row, that's also equal to 0. Okay? So basically, since z is the basic variable for the first column, I'm going to write z over here as well to indicate that z is the basic variable for the first column. Okay? And the value of z is exactly equal to 0, okay? Which is the same right-hand side value. The value of x3 is equal to 6, and if I look at the second row, the right-hand side is also 6. So as a result, x3 will be the corresponding variable here. Okay? And finally, x4 is the second basic variable. Its value is equal to 2. If I look at my tableau, then again, 2 is exactly the value of x4, which is the same right-hand side value. Okay? So as a result, in my tableau, I can read the values of z, x3, and x4 directly from the right-hand side. Okay? The value of z is equal to 0, the value of x3 is equal to 6, and the value of x4 is equal to 2. Okay? So this is my first basic feasible solution. Now let me go back to my picture. So what does this basic feasible solution correspond to in this picture? Well, we know that there's a one-to-one correspondence between basic feasible solutions and corner points, right? Okay? So what's the corresponding corner point in this picture? This is not too hard, so 0, 0, exactly, right? So I'll just look at the first two components. So this is my exact starting corner point. Okay? And indeed, the objective function value is equal to 0. Okay? So here is what the simplex method does. So we now have an initial basic feasible solution, okay, starting basic feasible solution, and the objective function value is 0. So now it asks the following question: is this the best basic feasible solution I can find for this problem? Okay, so is this the best I can do? Well, if you look at the picture, obviously the answer is no, right? So there are better solutions. So the question is, how can we find this out by just looking at this tableau? Okay, so think of that picture as just a sort of just to help you understand what's going on, but essentially this is what we're working with. Okay, so pretend that this is the only information we have. Okay, so the question basically is the following: so can I actually obtain a better objective function value by moving to a different basic feasible solution? Okay. Now, to answer that question, let me just go back to my current solution. In my current solution, both x1 and x2 have a value of 0. Okay? So what I can do is the following. I can try to increase x1, okay? Or I can try to increase x2. Okay? So these are my currently non-basic variables. So by increasing their values, I'm going to try to make them basic, basically. Okay? So by trying to improve their values from 0, I'm going to try to sort of turn them into a basic variable. So let me just look at row 0. So by the way, this is called row 0, row 1, and row 2. So row 0 corresponds to the objective function. Let me write that down. So I'm going to call it row 0 from now on. So this one is row 1 and row 2. So if I look at row 0 tells me that z is equal to minus 3x1 plus 2x2. Okay? And currently, both of these variables have a value of 0, as a result of which z is equal to 0. Okay? However, for example, if I increase the value of x1 from 0 to a positive value, and keeping x2 equals 0, so what happens in that case? So if I increase x1, then the value of z actually goes down, right? Okay? And that's not something I want, because I want to maximize the objective function. Okay? So as a result, increasing x1 does not really help me. Okay? On the other hand, if I increase the value of x2 by keeping x1 equals 0 still, okay, then increasing x2 will increase the value of z. Okay? So as a result, by looking at row 0, I realize that if I increase the value of x2, which currently has a value of 0, then my z value will also increase. Does that make sense? Okay? So as a result, I just discovered that by trying to increase the value of x2, I can actually obtain a better objective function value. Okay? However, there's one thing I need to be careful about. So basically, I can try to increase the value of x2, okay? But if I change the value of x2, if I look at row 1 and row 2, then that also affects the values of other variables, basically, right? Okay? So if I look at, for example, row 1, if I increase the value of x2, then the value of x3 will change, okay? Because I have to satisfy this equation. And similarly, if I change the value of x2, then the value of x4 will also be affected, okay? So as a result, I cannot really increase the value of x2 in an uncontrolled way in some sense, okay? So I need to have some control over the other variables as well. And that control is nothing but I need to make sure that I stay feasible for my problem, okay? So since I change the value of x2, the values of other variables may also change. So I need to make sure that I still maintain feasibility, okay? I'm going to try to be more specific now. So let me say that by row 0, increasing x2 by 1 unit actually increases z by 2 units. Why is that true? Well, because of the equation form of row 0, basically, right? So z is equal to minus 3x1 plus 2x2. So if I increase x2 by 1, then z will increase by 2, right? Okay. So the question basically is the following. So how much can we increase the value of x2? And remember, so we still keep x1 equals 0. Because increasing x1 does not help us. Okay, so I will still actually keep x1 equals 0. And I will try to increase the value of x2. And now the question is how much can I increase that? So the answer essentially is the following. So we have to maintain feasibility. I'm going to explain what I mean in a minute. So let me look at row 1. Okay? If I look at row 1, so let me write it in the equation form. So I have minus 3x1 plus 3x2 plus x3, and the right-hand side value is equal to 6. So I always have to satisfy this equation, basically. Okay? And since I'm keeping x1 equals 0, I can simply get rid of this. Okay? So the value of x1 stays at 0. That does not change. But now note that if I increase the value of x2, which is currently 0, then the value of x3 will also be affected, right? Okay? And it's actually affected in the following way. So x3 is given by 6 minus 3x2. Okay? So which means that if x2 is equal to 1, then x3 will be equal to 3, basically, right? Okay? So the value of x3 depends on x2. So what I want to do is I want to increase x2 as much as possible. Okay? But at the same time, I want to make sure that the value of x3 also remains non-negative. Okay? Why is that? Because if x3 is negative, then I lose feasibility. Okay? So as a result, essentially, I have the following condition. I have to make sure that 6 minus 3x2, which is the value of x3, should remain non-negative. Is that clear? Okay? So this actually gives me a bound on x2. Okay? So what does this imply? This implies that x2 cannot be more than 2. So by looking at the first equation, this basically tells me that if I increase x2 up to 2, then I'm still fine. But if I want to increase x2 beyond 2, then in that case x3 will be negative and I'm going to lose feasibility. Okay? So which means that if I want to sort of maintain feasibility for the first row, then the best I can do is increase x2 up to 2. Does that make sense? Okay? I'll just do the same thing for row 2. So let me first write down the equation again. Minus 4x1 plus 2x2 plus x4 in this case, and the right-hand side is 2. So once again, x1 is 0, so this part disappears. Okay? And again, from this relation, the value of x2 also affects the value of x4. Okay? So which implies that x4 is given by 2 minus 2x2. And once again, by the same reasoning, I want to maintain feasibility, right? So I want to make sure that the value of x4 remains non-negative. So as a result, I need to make sure that this expression should be greater than or equal to 0. Okay? Now, what does this imply on x2? x2 should be less than or equal to 1. So let's try to understand what this means. So if I look at row 1, okay, row 1 tells me that I can increase the value of x2 up to 2, and I will still have x3 non-negative, basically. Okay, I will still have a feasible solution. If I look at row 2, that tells me that I can increase x2 up to 1, and I will still be feasible. Okay? And remember, I want to maintain feasibility for all rows, basically. Okay? So what's the best I can do? So which one determines the value of x2? Well, basically, since this is a sort of more strict requirement, then the best I can do is increase x2 up to 1. Okay? In other words, if I increase x2 up to 2, then I'm fine with this constraint, but this one will be violated. Okay? So this one will have a negative value of x4, and I don't want to do that. So since this is more restrictive than this one, so this tells me that x2, the best I can do is increase x2 up to 1. Okay? Let me just go back to my picture again. And let's see what's going on this picture. So essentially, right now we're at the origin. Okay? And this is the first constraint, and this one is the second constraint. Okay? So the simplex method tells me that I have to increase the value of x2, so which means that I have to go in this direction, basically. Okay? So what I'm doing is the following. So I want to go in this vertical direction. How much can I go without violating my constraints? Okay? So if I look at the first constraint, well, the best I can do is go up to 2. Okay? If I look at the second constraint, the best I can do is go up to 1. Okay? And since the second constraint actually gives me more restrictive bound, then the best I can do is move up to this point, basically. Okay? So that's exactly what we did so far. Okay? So we're trying to increase the value of x2, and we're trying to decide how much we can increase x2 while still being feasible for the problem. Okay? For the first constraint, I can increase up to 2, but for the second one, I can only increase up to 1. Okay? So since I want to remain feasible for all constraints, then the best I can do is this point right here. Okay? That's exactly what we're going to do. Is that clear? So that's the picture. Okay? All right, so row 2 gives us the most restrictive bound. Bound on x2. So I want to increase x2 as much as I can, but I also want to maintain feasibility. So if I want to satisfy both of these objectives, then I should increase x2 exactly up to 1, basically, right? Okay? By increasing x2 exactly up to 1, I get the most increase in the objective function, and I still have feasibility for my problem. Okay? All right. Now let's see what happens when x2 is exactly equal to 1. If x2 is exactly equal to 1, then the value of x4 becomes 0, basically, right? So when x2 is equal to 1, the value of x4 becomes 0. So in the previous example, x2 was a non-basic variable with value 0. x4 was a basic variable with value 2. In the new solution, x2 will have a value of 1, which is positive, but x4 will have a value of 0. Okay? So now x2 will be my new basic variable, and x4 will be my new non-basic variable. Okay? So now I'm going to change my basic and non-basic variables. Okay? So x2 will be the new basic variable. And x4, which gives me the tightest bound on x2, will be the leaving variable. Will be the new non-basic variable, sorry. So we simply say that x2 enters and x4 leaves. Okay, so of course entering and leaving is with respect to set of basic variables. So x2 is the entering basic variable and x4 is the leaving basic variable. So x2 was non-basic and becomes basic. x4 was basic and now becomes non-basic. Okay? Now let me come back to this picture again. And let me try to illustrate that, all these sort of calculations that we have done, we could have done directly using this table. Okay? And how do we do that? Well, basically, my goal is to increase the value of z. Okay? And z only appears in the first row. So if I look at the first row, I have z plus 3x1 minus 2x2 equals 0. Okay? If I put everything on the right-hand side and leave z alone, then I have this equation. Okay? And from this equation, I immediately say that if x1 increases, then z decreases. But if x2 increases, then z increases as well. So which means that if I have a negative coefficient in row 0, that becomes a positive coefficient on the other side. Okay? So as a result, if there's a negative coefficient, then I should increase that variable. I can say that right away. Let me repeat that again. So if I look at row 0, and if I write in the equation form such as this one, note that the coefficient of x1 is minus 3, which is the negation of this one. And the coefficient of x2 is 2, which is negation of this one. Okay? So which means that if I have something negative here, then that's good for me. Right? Why? Because minus 2 becomes actually plus 2 on the other side. Okay? So which means that if I want to increase x2, then z will increase as well. Okay? So then I make the decision as follows. So is there a non-basic variable that I want to increase? The answer is yes, if there's a negative coefficient, okay, in row 0. The negative coefficient in row 0 tells me that if I increase that variable, then z will increase as well. This is clear, right? Okay. All right, so that tells me that I should increase the value of x2, which was our first decision. The next question is, how much can I increase x2? Okay, and that's also pretty easy. So what you do is the following. You look at the column underneath x2, and you look at the right-hand side values. Okay? So what you do is, you take 6 and divide it by 3, which is the column underneath x2. So 6 divided by 3 is exactly equal to 2, which is the first bound here. Okay? And then similarly, you divide 2 by 2, that's the second coefficient underneath x2, and 2 divided by 2 is equal to 1, and that's exactly the second bound here. Okay? So which means that instead of writing them down, we could just do those equations, those operations directly on this table, which is what we're going to do from now on. So as a result, if I want to sort of know the bounds on x2, then I'll just look at the ratio of 6 to 3 and 2 to 2. Okay? And which one is smaller, whichever is smaller will tell me the exact bound on x2. Is that clear? So, all right. So as a result, we just sort of found a better solution. And now how do we continue is the next question. Yes?
What if we don't take x1 as 0? Couldn't we increase it to, if we increase x1, x2 will also, x2 can increase to like 3. We can take x2 3 and x1 1, and thus z will also increase.
That's a good question. So now the method only looks at increasing one variable at a time. Okay, it never increases more than one variable. Okay, so it only looks at each non-basic variable one by one, and it has the following question: should I increase this non-basic variable or not? Okay, so the problem is that if I want to increase x1 without changing x2, then I'm going to make z worse basically. Okay, but if I want to increase x2 without changing x1, then I'm going to make my z better. Okay, so as a result, since we're increasing only one variable at a time, the answer is that x2 is the correct variable to increase for now. Okay, so in the next solution, we're going to see that we should also increase the value of x1. Okay, but we do it one at a time. Okay, one variable at a time. Okay, so now this is crucial, so I just want you to pay attention to me. So remember, our basic variables were z, x3, and x4. Okay, and x2 was a non-basic variable in this case, and our analysis just told us that x2 will be the new basic variable and x4 will be the new non-basic variable. Okay, so what does that mean? Well, in row 2, okay, the basic variable x4 will be replaced by x2. Okay? So what we do is the following. I look at the column of x2, and I look at the row of x4, and it's this entry right here. Okay? So now what I'm going to do is I'm going to pivot on this entry, just like you did in linear algebra. Okay? So I'm going to turn this equal to 1, okay? And I'm going to try to make this equal to 0. Okay? And by doing that, now I'm going to try to make this column look exactly like this column right here. Okay? So the column underneath x4 was 0, 0, 1. Now I'm going to try to make this column look exactly like 0, 0, 1. Okay? So how did I determine this entry? I'm looking at the entering variable, I'm looking at the leaving variable, and the intersection gives me the entry that I should pivot on. Is that clear? Are you still with me? Okay. So as a result, now what I'm going to do is x2 is the entering variable, x4 is the leaving variable, and I'm going to try to pivot on this entry. So essentially I'm going to try to make it equal to 1, and I'm going to try to zero out these terms, and if I do that, the new column underneath x2 will be the same as the old column underneath x4. Okay? So that the roles of x2 and x4 will change, basically. Okay? Alright, so let's do that. Well, if you pivot on this entry, so let me do it over here. So as I said, the first column never changes, so I'm going to have 1, 0, 0. So what's the first step? Well, I should divide row 2 by 2, basically, right? Okay. And if I do that, I have minus 2, 1, 0, 1 over 2, and the right-hand side value is 1. Okay? What's the next step? So I'm going to multiply this new row 2 by minus 3 and add it to the old row 1. Okay? And if you do that, you have 3, 0, 1, minus 3 over 2, and the right-hand side is 3. And finally, I'm going to take this row and add it to row 0. And if I do that, I have minus 1, 0, 0, 1, and the right-hand side value is 2.
You are not changing values of Z, never.
Well, we are changing values of C. We're not changing the first column. Okay? The first column is always 1, 0, 0. Sorry?
Why is it like that?
Because Z is the extra variable that I defined, and Z always corresponds to the first row, so I never play with Z. Z is always there. I only change x3 and x4 if necessary. Okay? So now I actually have a different solution. Okay, so now let's try to understand the new solution. Again, the corresponding variable here is Z, that does not change. The corresponding variable in the first row, which is given by 0, 1, 0, so the second column of the identity matrix, I still have x3 here. And if I look at the column underneath x2, I have 0, 0, 1, so the third column of the identity matrix, so x2 is the corresponding variable here. Okay? So if I compare these two tableaus, basically, x3 was basic, x3 is still basic. x4 was basic over there, x4 is non-basic here. x2 was non-basic, and x2 is basic. Okay? Now, if you look at these two solutions, there's exactly one basic variable in common, right? x3 is basic here, and x3 is basic over there as well. So these two are adjacent basic feasible solutions. Okay? So what's the new solution? Let's try to figure that out. So in my new solution, x1 is equal to 0 because it's non-basic. What's the value of x2? Well, again, if you just go back to this picture, the value of x2 is exactly equal to 1, right? So that was the best I could do because I want to increase x2 up to 1. And the right-hand side value of second row gives me exactly the new value of x2. Okay? So as a result, the new value of x2 is equal to 1. What about x3? x3 is equal to 3. Again, that's given by the right-hand side value. And what about x4? x4 is equal to 0. Okay? Now, what's the corresponding value of z? So my variables are x1 is equal to 0, x2 is equal to 1. And if you plug in these solutions into the objective function, you're going to get 2, right? And indeed, if you look at the right-hand side value, you get exactly equal to 2. So z is equal to 2. Well, we started with an objective function value of 0. So now we have an objective function value of 2, which obviously is better than 0, right? Okay? So we found a better basic feasible solution. So our basic variables, in this case, are x3 and x2. Our non-basic variables are x1 and x4. So what's my B matrix in this case? Let me just go back to that picture. So I'm going to look at first x3, then x2, right? So I'm going to take the third column and then the second column. So what's my B matrix? So I'm going to look at the columns of x3 and x2, right? So 1, 0 is the first column. And how about the second one? 3, 2, exactly. So that's my B matrix. How about my non-basic or AND matrix? So I'm going to look at the first and fourth columns. So -3, -4, and 0, 1. Okay? So basically, I'm going to set all my non-basic variables to 0. And my basic variables, which are given by x1 and x4, is b inverse times little b. x3, x2, thank you, yes. Okay, sorry about that. And if you take the inverse of b, you get 1 minus 3 over 2, 0 and 1 over 2. And you multiply by little b, which is 6 and 3, and you get 3 and 1. Well, indeed, the value of x3 is equal to 3. The value of x2 is equal to 1, and that's exactly what we had over here as well. Okay? So indeed, we actually found a new basic feasible solution now. Okay? Our basic variables are x3 and x2. Our non-basic variables are x1 and x4. And the new objective function value is equal to 2. Yes?
I think that's why B and
Well, because my basic variables are x3 and x2 in that order. Why in that order? Because x3 is the basic variable for the first row, x2 is the basic variable in the second row. Okay? Then I'm looking at first the third column of A corresponding to x3, then the second column of A corresponding to x2. Okay? So that's my B matrix. And if I do these operations, I get exactly the same solution as this one. Okay? So in other words, actually by doing those operations, we're already computing the values for the new basic feasible solution. So we don't need to do this extra step. Okay? So the Tableau is already doing it for us. Okay? So now the question is the following. First of all, what is the corresponding solution in the picture? Well, in this new solution, x1 is still 0, x2 is equal to 1, right? So what does it correspond to? Well, it's exactly this point right here. Okay? So we start with the origin, and now we actually move from this point to a better objective function value, to a better corner point. Okay? So now we can ask ourselves the same question. So is this an optimal solution? No. So essentially, just like we did in the first basic feasible solution, I'm going to look for a negative coefficient in row 0. Okay? So right now, my non-basic variables are x1 and x4. Okay? If I increase x4, okay? So what happens if I increase x4? Z will decrease, basically, right? Because z and x4 have the same signs. Okay? On the other hand, if I increase x1, then z will increase as well. Okay? So now, as a result, I need to increase x1. Okay? So which means that x1 will be my new entering variable. Okay? So x1, which was non-basic in the solution, will now become basic. Okay? So let me write that down. So x1 is the entering variable. So the next question is, now I know that if I increase the value of x1, I will get a better objective function value. So the question is, how much can I increase x1? Okay? And for that, I need to sort of make sure that I maintain feasibility, right? So I need to make sure that I don't violate feasibility, because if I change the value of x1, then the values of other variables will also change. Okay? So I cannot really increase x1 as much as I want. I need to make sure that the other variables also stay non-negative. Okay? So once again, let me just go back to my first row in the second solution. So the question is, how much can we increase? Well, if I look at row 1, so by row 1, so 3 times x1 plus x3 minus 3 over 2x4 is equal to 3. Okay? And x4 is non-basic, so I'm going to still keep it at 0. So that doesn't change. So this implies that the value of x3 depends on the value of x1 in the following way. So 3 minus 3x1. So which means that if I increase x1, then the value of x3 will go down as well. Okay? But I want to make sure that I remain feasible, so I need to make sure that the value of x3 remains non-negative. So what does this imply? This implies that x1 is to be less than or equal to 1, basically, right? So I cannot increase x1 by more than 1, because if I do that, then x3 becomes negative. Okay? What about row 2? So let me first copy row 2 as well. Minus 2x1 plus x2 plus 1 over 2x4. And the right-hand side value is 1. Again, I'm keeping x4 equals 0. Okay, x4 is non-basic, and I'm not changing that. So we have the following relation. x2 will be given by 1 plus 2x1. Okay? So currently the value of x1 is 0, right? And I want to increase the value of x1. Well, how much can I increase the value of x1? So if I want to make this greater than or equal to 0, this implies that x1 has to be greater than or equal to minus 1 over 2. Okay? But obviously x1 is already non-negative, right? So which means that this is always satisfied. Okay? In other words, if you look at this sort of relation here, if I increase the value of x1, the value of x2 also increases. Okay? So which means that by increasing the value of x1, I can never make x2 negative, basically. Okay? Increasing x1 also increases x2, so as a result, essentially, which means that there's no restriction from the second row. Okay? So the second row does not give me any restriction at all. Okay? So then what's the best I can do? So I can set x1 equals 1, basically, right? So now let me just go back to my tableau again. So I told you in the first place that we didn't need to do this operation because we can do it directly from the tableau. So now x1 is my entering variable. Okay? And I'm going to ask myself, well, how much can I increase x1? So for that, I need the ratio test. So I'm going to divide 3 by 3. That gives me 1. So 1 divided by minus 2, which gives me minus 1 over 2. But essentially, the second row does not give me any restriction on x1. Okay? So which means that when I look at the ratios, I only need to consider positive entries, basically. Okay? Those are the only ones that actually give you a restriction. Okay? So as a result, when you look at the ratios to determine how much you can increase x1, you can simply get rid of the ones that are negative. Okay? Why is that? Because essentially, if you just look at this second row, row 2, if I increase x1, then the value of x2 will also increase. Okay? So which means that row 2 does not give you any restriction on the value of x1, on how much you can increase x1. Does that make sense? Yes?
In the first sentence column, we can't have a 0, right?
Sorry?
In the x1 column, we cannot have a 0.
You mean somewhere here or?
3
It can be 0 as well, actually. Okay, that's a good question. So if, for example, if this is equal to 0, what does that mean? Well, if this is equal to 0, then that means that the value of x2 does not depend on x1 at all, right? Okay? So which means that I can increase x1 as much as I want, and x2 will not be affected. Okay? So which means that when you look at the ratios, you should only look at the positive entries underneath. Okay? You should only look at the positive entries, because if you have a 0 entry or negative entry, that means that those corresponding rows do not give you any restriction on the value of x1. Okay? So as a result, now I'm going to try to set up my new solution, my new tableau. So x1 enters, which variable leaves in this case? Well, since we have the restriction from the first row, x3 will be the leaving variable, right? Okay. So what's my new pivot? I'm going to look at the column of x1, I'm going to look at the row of x3, and this is going to be my new pivot, basically, okay? So now I'll just do one more operation. So this is my new tableau, z, x1, x2, x3, and x4. And I have the right-hand side. So as I said, the first column never changes. I have 1, 0, 0. All right, what's the new row 1? So now I'm going to pivot on that entry, right? So what does the new row 1 look like? Everybody knows what pivoting is, right? Does everybody know what pivoting is? Okay. So what am I going to do? So I need to divide it by 3, right? So I need to make that circled entry 1, and to do that I'll divide it by 3. And if I do that, I have 1, 0, 1 over 3, minus 1 over 2, and the right-hand side value is equal to 1. Okay? All right, so now I need to zero out the other entries in the column of x1. Okay, for example, I can multiply this new row by 2 and add it to row 2. Okay, and if you do that, you have 0, 1, 2 over 3, minus 1 over 2, and the right-hand side is 3. Okay, and finally, if I take this row 1 and add it to row 0, then we have the following. I'm going to have 0, 0, 1 over 3, 1 over 2, and the right-hand side value is 3. Now, what's the variable for the first row? Row 0. So it's going to be z. What's the variable for the second row? So it's going to be x1. What about row 2? It's going to be x2, basically, right? So what are my basic variables? x1 and x2. And what are non-basic variables? x3, x4. What's my B matrix? So I'm going to look at the columns of A corresponding to x1 and x2. So it's going to be minus 3, 3, and minus 4 and 2. Okay? I'm not going to write down the AND matrix because we don't need that. And if I indeed solve for xp, it's given by b inverse times little b, and b inverse is given by 1 over 3, minus 1 over 2, minus 1 over 2, 2 over 3, and multiply by little b, 6, 2, and you get exactly 1, 3 again. So xp, which is given by x1 and x2, has the value of 1 and 3, and indeed x1 is equal to 1, and x2 is equal to 3. So we get exactly the same solution again. Okay, so this implies that my basic variables are given by x1 and x2, and their values are 1 and 3. And my non-basic variables, which are given by x3 and x4, and their values are 0. Now, what's the value of z, the objective function? Well, so my variables are 1 and 3. Okay, if you just plug in 1 and 3 in the objective function, you have minus 3 plus 6, which is equal to 3, and 3 is exactly the same as the right-hand side value, okay? So what have we done so far? Well, the new solution is given by 1 and 3. And what does that correspond to? Well, it's exactly this point right here, basically, right? Okay? So once again, we started with this solution. We moved to this solution, which is an adjacent corner point, or adjacent basic feasible solution. And from this solution, we actually moved on this edge to this solution. And again, we moved to an adjacent basic feasible solution, right? Okay? So now we know from the picture that this is the optimal solution. Okay? So the question is, how can we also say it from this tableau? Well, I mean, the idea is pretty simple, as I said. So you're going to look at the non-basic variables. Okay? So what are my non-basic variables in this case? x3 and x4, right? So what happens if I increase x3? Well, if I increase x3, then z will decrease, right? Okay, so there's no point in increasing x3. What happens if I increase x4? Again, z will decrease. So as a result, I cannot find a better solution. Okay, so this is the best I can do. So since there are no negative coefficients, in row 0, this basic feasible solution is optimal. So as a result, we actually found an optimal solution. The optimal solution is given by x1 is equal to 1, x2 is equal to 3, x3 and x4 are equal to 0, and the objective function value is equal to 3. Okay, so the optimal value will be equal to 3. So let me just quickly, yes?
What happens if we start with x1, right? If we start with x2 and we increase it, but if we start with x1 and start to decrease it at first?
You mean here?
No, from the beginning.
So this is the beginning.
Then we may start with decreasing x1. Is it possible?
Okay, so that's a good question. So, so what your friend is suggesting is the following. So we know that if we increase x1, then z will decrease, right? Because of this. So she says, why don't we decrease x1 actually? Okay, if we decrease x1, then z will increase, right? Well, the problem is x1 is already equal to 0. Okay? If I decrease x1, x1 will be negative. Then I'm going to violate feasibility. I cannot actually make x1 smaller than 0. Okay? So for non-basic variables, I can only increase them. I can never decrease them. Because if I decrease them, then I'm going to violate feasibility, right?
So we cannot change the order of increasing like x2, x1. At first we have to increase x2.
So once again, since non-basic variables are equal to 0, okay, and since 0 is a lower bound on your variables, because all the variables are non-negative, so you cannot go down, you cannot go below 0, okay? You can only increase your variables from 0.
If x1 and x2 both minus sign values, can we start with any of them?
That's a good question. So we're going to see such examples later on. But in principle, if there are two negative coefficients, then you can increase any one of them. Okay? So either one will actually give you a better solution. Okay? Other questions? So once again, I mean, the idea is pretty simple. So you start with the basic feasible solution. Okay? And then you look at row 0, because the coefficients in row 0 determine whether you can get a better solution or not. Okay? For a maximization problem, if you have a negative value, then that means that by increasing that non-basic variable, you'll get a better objective function value. Then you decide how much can I increase that variable. For that, you do a test, basically, a ratio test. So you divide 6 by 3 and 2 by 2, and whichever is smaller actually tells you how much you can increase. Then that determines the leaving variable. Then, it also determines which entry you're going to pivot on. And if you do that, you end up with this solution. So here again, there's a negative coefficient. So I want to increase x1. Again, I do a ratio test. Okay. So I only look at the positive entries here, though. Okay. Those are the only ones that sort of control x1, control the increase of x1. So in this case, the minimum ratio is equal to 1. then that also determines x3 will be the leaving variable. And if I pivot on this entry, then I obtain the last tableau. And in the last tableau, which corresponds to the third basic feasible solution, there are no negative coefficients in row 0, which means that this is the best I can do. Okay? Yes?
If this is a minimization problem, then we are going to make it up until we have no positive values in that.
Exactly. That's very good. So that's going to be our next example. If I wanted to decrease the objective function, okay, then of course instead of increasing x2, I will be better off increasing x1, because increasing x1 actually decreases the value of c. Okay? So the only difference between minimization and maximization is that in maximization, you actually look for a negative coefficient. In minimization, you will look for a positive coefficient, basically. Okay? Any other questions? I'll see you on Thursday.